Hello, everybody. My name is Konstantin Osipov, and today I'm going to talk about the updates we've done to the topology and schema changes in 6.0. So first, a few words about me. I've been working on databases for a while. Besides databases, I regard myself a normal person. I like swimming, breathing, and spending time with my family. So today I'm going to iterate over the advancement in metadata management we've made in the past year. While preparing this presentation, I actually realized how much has changed since the old good times of on-premise. Nothing you will learn today is critical if you use Scylla Cloud. We will run the system for you and will consume our own dog food. If you are familiar with Scylla Raft Saga, I recommend, if you're not familiar with Scylla Raft Saga, I recommend the previous episodes of the show, which we've begun running since 2021. And before I continue, I will quickly go over the basics of consistent metadata management. What kind of problem is it is, and why we are doing it, while we are trying to make the data management consistent in Scylla. So what is this consistency all about? It's about the model of concurrent interaction between the client and the database. A strongly consistent system, when interacting with the client, guarantees the freshness of the current state. This creates an illusion of like sequential interaction. One client, the latest state, the update, then the next client, and so on. An eventually consistent system is allowed to provide the user with not up-to-date data, eventually reconciling changes of concurrent users into a single state. And as you can see from this illustration, there is a difference in how eventually and strongly consistent systems interact internally. Like eventually consistent systems are allowed to return positive response to the client before propagating the data to the rest of the cluster. Strongly consistent systems, they need to reconcile the data within the cluster, and only then they can respond to the client. Another difference is that eventually consistent systems, they are allowed to operate when some part of the cluster is not available. While strongly consistent system, obviously, since they need to reconcile the data before, they need to have the majority of the nodes in the cluster available to execute the operation. So a while ago, we observed that Scylla, while being part of the Cassandra family, has two types of data, like the user data and the data about data, which we call metadata. It's the schema definition, it's the state of the cluster, who are the members of the cluster, the format of the tables, and so on. So these are two different kinds of information. While client data is replicated and partitioned, meaning that every part of the cluster stores its own fraction of the data, partition or a shard. The metadata usually needs to be stored on every node of the cluster. And also there are differences in the frequency of changes, like client data changes frequently, the metadata changes infrequently. So while Scylla is an eventually consistent database, it makes sense to move metadata to strong consistency to make sure it's consistently replicated to every node in the cluster. This also allows us to sort of bridge the gap towards elasticity, make the node operations, the scaling of the cluster fully automatic. So back in 2021, we embarked on a journey to bring in Raft, an algorithm and a library we implemented internally to replicate any kind of information across multiple nodes. So what's the idea of this replicated state machine? Suppose you had a program that you wanted to make reliable. And this program would be deterministic. If its execution depended on the input, but did not depend on the environment. So if it produced the same, if it is consumed the same kind of inputs, it would produce the same kind of outputs. How can you make this program distributed and reliable in the distributed sense so that multiple nodes can run this program and get the same results? The idea of Raft is that you put every input of this program into a replicated log first. Here we have the log in green on the picture. And once you've made sure that every copy of the log has the same sequence of the commands, then you can feed these commands to the local state machines for execution. And as long as the state machines gets the command in the same order, they get the same input, they're going to produce the same output. The consensus module is responsible for replicating this data and for making sure that when nodes come in and out, the whole system continues being reliable. And this kind of system can make progress as long as the majority of the servers are up and can communicate with each other. So in case of a cluster of 3 nodes, it requires 2 nodes. Cluster of 5 nodes, it requires 3 nodes to be live, to be available. Initially, we put the schema into this kind of replicated state. So as you can see, initially, mostly the key spaces, tables, and columns information was replicated through Raft. But in 6.0, we greatly expanded on the amount of information we store in this replicated state machine. Besides expanding the schema information, and I'm going to talk about this in more detail later, we moved topology over Raft. And you probably know that the whole tablets project and the tablets coordinator, tablets load balancer are also built using the centralized topology coordinator. So if you haven't listened to Avi's talk, I recommend watching the recording, so where he speaks about that. We also preserved backward compatibility with old Scyllas so that the old drivers, the old clients can get the information when they expect to get it. The way we changed the topology operations when we based it on the centralized stuff state is we also converted it to like a central role. If like in 5.0, in order to execute addition of a node or removal of a node, you need to find the node that would drive the progress, and it could be any random node in the cluster. In 6.0, there is the central role, which we call the centralized topology coordinator, which drives the topology change forward. If anything happens to that node, the failure doesn't need any DBA's attention because there is a coordinator failover, and we will continue running the operation on the next node that would fail over the coordinator state. All of the operations that clients, or in this case DBAs, request, they create a work queue, and the topology coordinator is allowed to provide some illusion of concurrency because multiple operations can be queued at the same time. They are not rejected, and can build a deterministic schedule, like optimizing the execution of multiple operations. So for example, with tablets, we can migrate multiple tablets at once. With cleanup, we can coalesce cleanups necessary for multiple node tool operations and so on. And like I already mentioned, in the event of the coordinator failure, a new node is automatically elected and the leader as the leader of the cluster, and continues to drive the topology work forward, continues to work off the topology queue, topology operator queue. The important part of it is that since the coordinator state is stored in this deterministic state machine, which is replicated across the entire cluster, the new coordinator can continue where the previous coordinator left off. So now let me go over some practical application of this design in 6.0 and begin with I want to begin with the improvements to schema changes that we introduced. You've probably heard about the feature in Scylla called the schema commit log. It's a dedicated commit log that runs on shard0, and it has different properties than the data commit log. So first of all, it's always durable. It's always sync right to disk. It has a different segment size. It allows bigger chunks of data to be written into a single segment. For example, if you have a large definition of a table, we by adjusting the segment size of the schema commit log, we allow these large definitions to be provided, and thus addressing the need of some of our clients who have very large table definitions. And in 6.0, we also moved the topology information. All of the topology tables that store this information, they're also made durable using the same schema commit log. This is important because we automatically get A, linearizability of these changes with schema changes, and B, the durability of these changes. So another important property is that there is no longer priority inversion between topology changes or schema changes and data operations. Since they used to be using the same commit log as the data, if there is an intensive work done on, on behalf of the client, some of the schema or topology operations could starve. Another change that we've made is changing the way we build a schema version. Schema version is an identifier that we use internally in cross-node RPC to understand that every node has the same version of the metadata. So whenever a table definition changes, it has to be rebuilt. And because of the eventual consistency, which allowed concurrent schema modifications, we used to hash all the tables to create a new version on each schema change. And since now schema changes are linearized, we can use a timestamp, a time UUID, a monotonically growing identifier to identify the schema, which is much faster and allowed us to increase the performance of schema changes like, tenfold on large. Most importantly, it's not quadratic anymore. Like previously, it had to go over all of the data. Now it just needs to look at one previous identifier. Another positive improvement is that we moved authentication and service level data to Raft as well. So now they are globally replicated, meaning they're present on every node in the cluster. Besides having to adjust the replication factor in practical installations, as you can see in the quote from Scylla manual that I'm making here, it was also a denial of service problem. If part of the cluster is not available, and this role definition was residing on these nodes, which are not live at the moment, it was possible that you couldn't connect to the cluster at all. Now, since the information is present on every node, you can obviously always connect as long as you can connect to any node. For service levels, we transformed from like polling model when we periodically refresh the service level information to trigger model. Whenever the service level information changes, we update the cache state and actualize the service levels. Now I'm going to cover some parts of the metadata we converted to strong consistency in 6.0. And to illustrate how tricky this transition can be, let me start with a little known feature in Scylla that's called feature negotiation. To ensure smooth upgrades, Scylla runs a negotiation protocol between the cluster nodes. Like a new functionality is only enabled when all of the nodes in the cluster support it. But how does the cluster know actually that the other nodes support the feature? Prior to Raft, it was propagated through gossip, and it would take time to propagate. The nodes were gossiping this information. When this information would settle, they would start the upgrade. But moving this data to Raft is also a feature. So we have a chicken egg problem. How do we quickly learn that the entire cluster supports the new feature that allows it to quickly learn about the new features? In order to implement this, we changed the node join procedure, and we transformed the join request so that it's now executed on behalf of the node by an existing member of the cluster. So this join information, which includes the features that this node supports, its niche, its cluster name, is sent to an existing member. Then it's being validated. Then the topology coordinator decides whether to accept the node or to not accept a node, to reject a node because it's saying it doesn't support some of the features. But the important part is that enablement of any cluster feature is now serialized with the addition of the node. So there is no race. It's not possible to enable a feature while adding in another node to the cluster. And we don't require the expensive gossip timeout for that. Another example is like this information about CDC streams, which is called CDC generations, which also used to be propagated via gossip, and now it's propagated via Raft. The same advantages here, like we don't need to sleep to learn it. The information propagates very quickly, and it's very reliable. So just if you don't know, CDC generation is information that allows the signal drivers that the existing CDC streams that where they reside, this information needs to be refreshed. So there are new CDC streams that they need to learn about. In 6.0, we also automated as a stable cleanup. Like the cleanup you have to run between topology changes. Why do you need to run this cleanup? Unless you do it, there is a possibility of data resurrection. If you perform, if you're, say, example, imagine you move the data from a node, and the streaming is succeeding, is running fine, but in the end, for some reason, the topology change fails. It is possible that the node which contains the old ranges would incorrectly serve queries that allow updates to these ranges, and in the end, the user will get the wrong data. So you do need to do cleanup if you plan to perform like subsequent node tool operations, and this is requested in our manual. Now we automate this process, do this internally for you, so you no longer need to worry about it. Most of the systems in Scylla, they switch to UUID-based host identifications. It's the host identifier we use in Raft, and it's way more reliable than IP addresses to basically understand which node we are talking to. When we establish a connection to a node, now we perform a kind of handshake, and this handshake includes the node's host ID, and it allows us to ensure that a node that was removed from the cluster, for example, cannot corrupt the cluster data with its queries, with its requests, because the rest of the cluster knows, even though it has the same IP address, for example, it has a removed host ID, so it's no longer a member of the cluster, and we need to ban it from the cluster. Similarly, we provide the DBAs with a safety net, and if a DBA by mistake tries to remove a live node from the cluster, we return an error. So it's only possible to decommission a live node. The end result is that ScyllaDB now officially supports safe, concurrent, and fast bootstrap. We no longer use skip wait for gossip to settle when bootstrapping. And this variable is simply, it's not used, it's ignored. I want to conclude my talk with a bunch of manageability improvements that we've made. We provided a new system tables for inspection of the Raft states. This information is mainly useful when troubleshooting and allows you to learn whether the node is in a good state, whether it has a group ID, whether it has it finished bootstrapping because it can vote. It's an indicator that it has finished bootstrapping. We added a couple of REST APIs to manually trigger some of the internal operations. It is also mainly useful for troubleshooting. And we added a whole new mode of starting Scylla nodes. It's called the maintenance mode. It allows you to start a node which is completely isolated from the rest of the cluster and manipulate the data on that node, for example, to fix it or to allow it to join, say, a different cluster, a new cluster. And the connection happens through a local file, local Unix socket, and we updated the SQL shell so to be able to connect to a Unix socket to support that. So with all that, how do you actually enable Raft in 6.0? You don't. It's always enabled, and I think it's probably the best and the main indication of the journey that we've concluded. So it's always on. We even deprecate and ignore the existing option, consistent cluster management. You can do whatever with it. You can set it true to false. It's not used. And I hope in the future, and as you can see with the tablets project, this is going to be a strong foundation for Scylla to build data consistency as well. This concludes my review of the latest and greatest in Scylla data and metadata management, and thank you, and hope to see you next year.